Hello MIT Beaverworks and everyone watching. We are Team Brailliance. Akshat, John, Riley, Retrieger, and I, Ivana, are here to present you with our capstone project, an affordable Braille reader. When thinking about ideas for our ASIC design, we wanted to make a product that would be viable, powerful, and most importantly, helpful. While brainstorming issues that we could solve, we narrowed it down to the lack of accessible resources to aid visually impaired people. There are three main parts to this. Number one, our website. Number two, our ASIC, or application-specific integrated chip. And number three, our physical Braille display. First, users will input text into our website's text-to-ASCII transcriber. ASCII converts text to numbers, and these numbers in the form of data will be sent to our chip. Our chip, stored in our Braille device, will convert this data into binary, or ones and zeros. This binary will send signals to our actuators or pistons that will move our Braille pins up and down. There you have it, our product. Simple, nuanced, and yet effective. Now, John will explain our website in detail.
Thanks, Savannah. I'm John, and I'm going to introduce the first phase of Brailliance, our website. Right now, I'm on our homepage where you can see some basic information about our processes. But next, we're going to move on to our text-to-ASCII transcriber. You can enter in any string of numbers, letters, or punctuation, and this tool will immediately convert it into ASCII. As Savannah mentioned earlier, this information will be sent to the ASIC chip and converted to Braille. Below the computer-based transcriber, we've got a simplified mobile option and some more details. The website also includes an interactive CAD display of our physical reader. Now, if you've got more questions, just check out our FAQs, and if you want to learn more about us, you can check out our biographies on this last page. And here's Riley to explain the ASIC itself.
Now let's take a look at the ASIC that powers our device. As of right now, it functions as a single refreshable Braille cell that translates an input string character by character. Before I begin explaining the process, here are some fundamental ideas. On the left is a typical Braille display cell, a 3x2 grid of dots. Each dot has two states, either raised or flat, therefore behaving similarly to a binary bit. For our purposes, we'll read the cell dots in the order shown in a diagram, going row by row from 1 to 6. For clarity, here's an example for the letter W. By assigning the flat dots to white dots as 0 and the raised dots to black dots as 1, reading out the cell dots provides us a 6-bit Braille alias for the letter. In this case, it would be 011101. In this way, every Braille character is able to be seen as a 6-bit representation. As seen from John's website demo, a TXT file containing your string in ASCII will be generated. Taking a maximum of 255 characters, the unused lines are filled with zeros. From JavaScript functions within the site, the first value will always contain the total number of output characters, which becomes crucial when telling our ASIC when to stop translating. Therefore, our ASIC begins from the second line, taking in the hex input and seeking out the assigned 6-bit aliases from a hard-coded table of hex to Braille pairs within the chip before sending it towards an output memory. However, it isn't always as straightforward. Capital letters have the same Braille display as their lowercase counterparts, as well as some digits following a similar logic. For example, the number 3 and the letter C both have the same Braille output. So to differentiate a capital or a digit, an indicator character must come beforehand, as seen in the example for the capital W. This results in 2 output characters being added to the output memory from a single input hex. This logic diagram is of our ASIC. The converter module sends a signal requesting a next available ASCII, which is sent to the converter to be translated into a 6-bit alias, finally getting stored into a first-in, first-out memory block to be outputted in the order of the input. The clock serves to create the timing of the process, while the reset restarts the process. Here is the output provided from the provided input. Each character is displayed for roughly 1.3 seconds and can be read as Hello BWSI. Notice that to represent the capital H, we first see the capital indicator before the actual Braille code for H, leaving more output characters than inputs. This will be seen in the following demonstration. For the sake of the simulations, we will use LEDs and FPGAs, programmable chips loaded with our HDL code to demonstrate our process. ASICs require a lengthy development process that isn't attainable within our program, leaving FPGAs as the next best option.
And here is our ASIC. With the massive amount of transistors, it comes out to be 400 microns by 400 microns.
Thank you, Riley. My name is Akshat, and I'll take us through the final phase of Brailliance, our Braille board. In lieu of a physical model due to the time constraints, we opted to make one on Blender. The left Blender window showcases the Braille setup program, which automatically generates a 15 by 3 pin Braille board for a total of 45 pins. The right Blender window showcases the Braille board regeneration program, which enables a user to input a TXT file with rows of 6-bit Braille characters and animates the pins by moving them up vertically if the corresponding bit is a 1. The 4x8-inch board is portable, has a power button, and also has a refresh button to generate the next set of 45 characters. The Braille board follows standard Grade 1 Braille conventions, which provides each character a Braille symbol. In the future, we will work on implementing Grade 2 Braille conventions, which adds hundreds of Braille characters to represent contractions and abbreviations. I have created a video to demonstrate the capabilities of our model and how it works.
With Brailliance, we hope to impact the 200 million visually impaired people who don't have any sort of access to assistive tech. Now, originally, this device would cost you up to $15,000, but now with Brailliance, we've reduced the price to just $300. But this isn't all we're planning on doing. We hope to implement multi-display cells, where instead of one ASIC powering one ASIC, we have one ASIC that can power multiple, and this would reduce the price even further. Now, we also hope to integrate speech-to-text into our website. Instead of just having text to your Braille reader, you can also have speech to your Braille reader. Now, the last thing we want to do is to create an app interface in order to create more portability and ease of use for our elderly users. If you have any questions, you can scan the QR code to go to the FAQ page on our website or email us below. Thank you so much for your time.